So welcome everybody to the session on quantum programming languages. So the first talk will be given by Bonan Zhou on an expressive assertion language for quantum programs.
Okay, thanks for the introduction. Good afternoon, everyone. I'm Bonan Zhou from Tsinghua University, and it's a great honor and pleasure to present our recent work on the expressiveness of an assertion language for quantum programs. And this is a joint work with Professors Feng, Ying, and Zhou. Okay. Although I may assume that most attendees to the quantum session and POPL conference are already quite familiar with quantum programming, I will still spend several minutes recapitulating the necessary backgrounds, including the formal definitions of these jargon terms, because I need to clarify the meaning. Is there a mic? I need to clarify the meaning of the expressiveness problem we have solved in this work, which can somehow be regarded as a small but very theoretical and fundamental problem. And then I will present the assertion language we designed, and finally, if time permits, I will have a brief overview of the technical proofs of the expressiveness, which is quite tedious, actually. And so in this work, we are studying a wide acknowledged and prototype quantum language named quasi, and the syntax of it is presented here, and we use a calligraphic letter E to denote a primitive quantum channel from a fixed set. For example, you may include unitary transformations drawn from a specific universal gate set. And we use the calligraphy letter M to denote a binary quantum merriment, which means the merriment has only two outcomes, true or false, and different branches in the if statement or the while loops, the loop body of the while loops may be executed depending on the merriment outcomes you obtain. Okay? So the denotational semantics of a program statement is associated with a quantum operation, which is denoted by S with double brackets. And such an operation is defined by induction on the structure of the program statement S. And you may notice that, okay, the calligraphy letter I here denotes the identity operation. And in the semantics of if branching and while loops, we use calligraphic letter T and F to denote the operation when obtaining the corresponding outcomes true or false in the guard merriment. Okay. Since we have encoded the probability of outcomes as the trace of the program state, because you may see that the quantum operation here is not divided by the trace of the post-merriment quantum states. So we need to sum up the program states of the two branches to obtain the final program state for the if branching statement. And this is quite similar to the case in probabilistic programs, but quite different from the classical programming. Okay? And it is similar for while loops, except for that the semantics of while loops involves an infinite summation, which can be proved to converge all the time. And as we will discuss later, such an infinity poses significant challenges in the establishment of the weakest precondition. Okay. So next we will step into the program specification. And essentially we use a Hoare style triple PSQ to specify the property of a program S, and where P, Q are commonly referred to as the precondition and the postcondition, both of which are quantum predicates formally defined as a Hermitian operator with eigenvalues bounded between 0 and 1, and as is a quasi program statement as defined before. And the validity of such a triple indicates that the expectation of marrying the precondition P on an arbitrary initial state rho is no larger than the expectation of the postcondition Q on the resulting state after executing S. Okay, is such an inequality. And similarly, we can define an order between quantum predicates, such as, and this order can be intuitively understood as an analogy to the logical entailment in classical logics, such as P implies Q if and only if Q minus P is positive semi-definite. So So given the program specifications and the order, we can now formally define the notion of weakest precondition as the valid precondition, which is weakest with respect to the lower order. Okay? So it is actually a theorem that the weakest precondition always exists, as you can obtain the weakest precondition by applying the joint operation of the semantic function to the postcondition Q. The proof is actually very simple by the Schrödinger-Heisenberg duality, which has been discussed at a presentation in Plan QC session the day before yesterday, if I remember correctly. Okay. And so a direct corollary is that the quantum weakest precondition calculus is complete from an extensional perspective. It is complete because the weakest precondition always exists, as the theorem suggests. But I will soon illustrate what does it mean from an extensional perspective. But before that, I need to introduce the notion of assertion language. I know there are various definitions of language, the jargon term, in different fields, such as the automata theory or something. But here, by a language, we mean a collection of formulas that are generated by at most countably primitive symbols and finitely many grammar rules. And a language is referred to as the assertion language if it is used to express precondition and postconditions. For example, in classical programs, we use first-order arithmetic logic as the assertion language. They are formulas involving only finitely many quantifications, arithmetic operations, and natural numbers as constant symbols, because natural numbers are the set of which is countable. Okay? And the set of variables should also be countable. And now we see something is from an extensional perspective, means we treat the precondition and postconditions as purely mathematical objects, such as the Hermitian operators we just discussed before. But from an intentional perspective, we need to express the precondition and the postcondition as formulas within an assertion language, for example, the first-order logic. Okay? So here is a table comparing the extensional and intentional assertions across different settings. And in classical programs, it is a common practice to adopt the first-order arithmetic logic. For example, the formula here exists y such that x equals 2 times y, describes a program state such that the assignment of x is an even number. And each predicate formula can be then interpreted as a set of program states satisfying the predicate formula, of course, but not vice versa, because not all such sets of program states can be expressed by a predicate formula due to the inherent computability limitation of first-order logic. So every intentional formulas can be interpreted as extensional objects, but not vice versa. And similarly, in probabilistic programs, it was Conan who first generalized satisfy or not predicates to measurable functions on program states. And a recent work presented on POPL'26 designed an assertion language for such measurable functions. And for quantum programs, as we formally defined before, quantum predicates are defined as Hermitian operators. And in this work, we design an assertion language to express such quantum predicates. Okay? And then a question on expressiveness arises naturally. Is there a non-trivial assertion language for quantum programs such that the weakest precondition always exists and can be expressed as a formula within the language? Of course, we may assume that the post-condition is formulable. Okay, so we put a further constraint here. We require the WP to be expressible instead of just the existence of the WP. And the answer is yes, and in this work, the core contribution is that we provide such an assertion language for quantum programs and proved its expressiveness. Okay. Okay, so next I will present our assertion language, and The syntax of it is presented here. And you may notice that the first two lines define the arithmetic and the Boolean expressions in classical propositional logic. And you may notice that we only include rational numbers as constant symbols because the collection of rationals is a countable set. Okay? Only countable set can be stored and manipulated on a practical computer. Okay? And the third line defines the coefficient formulas where a lot of special constructs are included. For example, the indicator function, which is denoted by a Boolean expression B with bracket. And such an expression evaluates to 1 if the Boolean expression is satisfied, or evaluates to 0 otherwise. And similarly, we support the supremum and the infimum over classical variables. And you may notice that the production between two coefficient formulas are not accepted as valid formulas. But we will discuss later that actually the alpha times beta can be expressed as a coefficient formula, provided that alpha beta are bounded below or something. Okay? Actually, the first three lines defines exactly the same assertion language for probabilistic programs presented at POPL 2021. And for quantum part, we are expressing quantum predicates, that is Hermitian operators, as linear combinations of generalized Pauli operators with coefficients expressed as the coefficient formulas defined before. Okay? That is our assertion language, quite simple, right? But actually, the proof of its expressiveness is very tricky and tedious. And next, okay, here is a concrete example. So you may see that the expression on the left, right is interpreted on the operation on the right. And here, the component surrounded by a blue box evaluates to x if the Boolean expression is satisfied, that is 2 times squared x less than 1, or evaluates to 0 otherwise. So taking supremum over all possible x can express an irrational number with square roots. Okay, it's quite straightforward to represent irrational numbers with the combinations of supremum, infimum, and indicator functions, and that's the trick. So next, we will step into the most challenging part, is the proof of expressiveness. And honestly speaking, the problem here is inherently tricky and tedious, so I will try my best to get across the primary intuitive ideas behind them, and I will omit many technical assumptions and details here, okay? Overall, the proof is constructive, which means we provide explicit construction of the weakest precondition for every program statement and the general postcondition per se, okay? And since the weakest preconditions for program statements other than the while loops are more straightforward and can be obtained by directly extending classical techniques, we will put a particular focus on the construction for the weakest preconditions of the while loop. When we first recall that from an extensional perspective, the weakest precondition of while loops can be obtained by applying the adjoint operation of the semantics function to the postcondition Q, which can be written in an expression including limit, summation, and unfold composition of a quantum operation, which is quite complicated, okay? So the first problem we need to address is that it seems infeasible to express the application of an unfold composition of a quantum operation to Q as a formula parameterized by n, okay? So the first thing we do is to reformulate the weakest precondition for while loops. And since Pauli operators form an also normal basis, so we can decompose the postcondition Q in the basis of a Pauli operators with coefficients being the inner products between Q and P. And the angle bracket here denotes the inner product. So the application of E on Q can actually be expressed as an expression, can be expressed as a linear combination of EQ with coefficients being the inner products. And similarly, for a composition of two quantum operations, it can actually be expressed as linear combination of one-time application of E to Q with coefficients being the product between scalars, because inner products are scalars. Okay, so we have eliminated the composition of quantum operations, but we introduce inner products and summations. And in general, the n-fold composition of a quantum operation can actually be reformulated in an expression with summation and inner products and a summation of n terms. Okay. So we will next study how to express these weird expressions, such as the summation, the production, the inner product or something, and the limit. Don't forget about that. And the first thing is that, the first theorem we present is that the summation and production can actually be expressed as coefficient formulas. The theorem states that for an arbitrary coefficient formula alpha x, where x is a free variable, such a formula actually represents a series. For example, in the below, alpha x equals x means represents a series 1, 2, 3, 4, since alpha 1 equals 1, alpha 2 equals 2, and so on. And for such a coefficient formula alpha x, if alpha x is bounded below, we claim that there exists coefficient formulas sum alpha x n equals to the summation of alpha I over I from 1 to n. And the similar results hold for production. For example, if alpha x equals x, which means it represents a sequence 1, 2, 3, 4, 5. So the summation of the n items is expressed in the formula n times n plus 1 over 2, which is universally known as the Gaussian summation formula. Okay? But in general, such a construction we need to use Gödelization. I will speak in a very intuitive fashion, and I may omit several details. We use Gödelizations to encode a finite sequence of rational numbers. And we take supremum of such rational numbers when the rational numbers are strictly less than the alpha I. So we use Gödelizations to encode the rational numbers and then take supremum of such rational numbers to obtain the desired value, because we're approximating the summation of the series from below by rationals. And the rational numbers are dense in reals. So the supremum is equivalent to the summation as we desired. Okay? And next, we need to express the inner product between two predicate formulas, that is linear combinations of Pauli operators. And this can be achieved by substitution. Because Pauli operators forms an orthonormal basis, then the inner product between the two summation actually equals to the summation of the product between the corresponding coefficient. And this can be seen as substituting each occurrence of pi in the first expression by the corresponding coefficient bi in the second expression. Okay, this is a kind of substitution, and we are substituting Pauli operators by coefficients. Okay? And here we may need to express the production between coefficient formulas, and this can be achieved by constructing a new coefficient formula, gamma x, such that the gamma x evaluates to alpha if x equals 1, and it evaluates to beta if x equals 2, because this is the definition of indicator functions. So by the previous theorem, we just take product alpha x2, we just obtain the same value as the alpha times beta. Okay? Of course, everything here is bounded, and I may omit the tedious discussion about. And finally, we can express the limit with the help of sup and inf. And for example, if you have a converging series represented by alpha x, you can first take infimum over uppercase n, and then take the supremum over the lowercase n. And with the help of indicator function, you can claim the lowercase n is larger than the uppercase n. So after you're taking the supremum and infimum in turn, you will get the desired value, the same as the limit. Okay. Of course, in this case, we need the alpha x to be non-negative, but in general case, we can actually show that the limit in the weak precondition for while loops can be expressed with the help of sub and inf in our assertion language. So we're now putting them together, and from an extensional perspective, we have the formulation and expression of the weak precondition for while loops. And now, actually, we can claim that the weak precondition can be expressed as the linear combinations of Pauli operators with coefficients being expressed as the coefficient formulas in our assertion language. So actually, the most tricks here are classical and have nothing to do with quantum parts. Okay? And you may notice that there are limits, there are summations, there are inner products, and we have discussed before they can be expressed. And it is worth noting that you may see that there is still one-time application of quantum operation E to each Pauli operator Pi. And such an E dagger P is expressible by induction. Why? Because actually the quantum operation E here is connected with the semantics function of the loop body or the merriment in the while statement. So we can prove by induction hypothesis that the E dagger P exists, because it's a common practice to assume that the weak precondition for the loop body and the merriment have already exist. And given the existence of the weak precondition for while body, for loop bodies, we then construct the weak precondition for the whole while loops. Okay? So very loosely speaking, we have complete our proof of the expressiveness. And so the conclusion is that we have designed an assertion language that is expressive for quantum programs. And a very direct corollary is that the weakest precondition calculus for quantum programs is complete from an intentional perspective. And since as far as I know, maybe our work is the first to present the intentional completeness results. Okay, it's a very elegant and concise theoretical result. Okay, and as an application, we have developed a sound and relatively complete quantum Hoare logic. And it is complete because there is an equivalence between the existence of loop invariant and the existence of the weakest precondition for while loops. So the relative completeness can be directly derived from the expressiveness of the assertion language. And now we are taking our assertion language to express the precondition and postconditions in Hoare triples. And okay, that's all. Maybe I'm talking too fast, and thank you. Any questions?
There is a question over there.
Hi, very nice talk. As far as I understand, this is based off of expectation satisfiability, which is the trace of the pre and post conditions. How do all these change when you consider complete satisfaction of projections, where a very analogy is the applied QHL versus the normal QHL? So how would projective satisfaction fit into all of this?
Oh, thank you for your excellent or valuable questions. And actually, the history that I first considered the completeness from a satisfaction or not based, which is also referred to as a predicate-based completeness. And then I come to the expectation-based reasoning. But as we all know that the Hoare logic, an elegant inference system for Hoare logic, only exists for expectation-based reasoning. I don't know whether, because you can hardly derive a complete inference rule about the if branching in a predicate-based manner. Of course, that is for the satisfied or not based, but you mentioned the projection-based ones. I haven't considered about it clearly, and I'm trying to, at the future work maybe. because it's quite difficult to design a certain language for projection, actually. You need to encode the coefficient or something. Thank you.
Thank you. Please, Robert.
So there have been a lot of proofs done using the original QHL and a bunch of its derivatives. And I'm wondering both if you've tried to do the same proofs and kind of how they compare just in terms of usability of the new logic, and also whether or not the sort of the nice syntactic structure of this logic makes it easier to mechanize.
Sorry, background please. I can hardly grasp which is your question.
So just in practice, is this as usable as proving things, or is it just sort of complete in theory, but harder to use? And also, can you mechanize it?
Oh, that's a very critical but valuable question. And actually, the motivation for designing an assertion language is for the purpose of practical usage. But actually, as far as I'm concerned, and I know that most assertion languages, except for the first order language for the classical programs, the assertion language for probabilistic or quantum programs language are often categorized in two classes. One is specially designed for practical purpose, such as the pass-thumb or something. And another class is designed for theoretical results, such as our work or the work on at POPL'26. And we can hardly achieve both for now. Okay.
So it's future work.
Maybe. Thank you.
We are running out of time. Sorry. Maybe we can keep it, because...
Oh, we can talk in person later. Thank you.
Keep it offline. So let's go to the next